The other part we stated the problem, and it's basically we need to pour some amount of liquid into 3 different containers. And the 3 containers have capacities A, B, and C, where A is the biggest. And they're all different. Okay. So some of these diagrams are pretty cool. Oh yeah, so you're saying they look like 3-digit numbers, right?
Yeah.
But they're actually just coordinates. So it's an equilateral triangle, yeah? And A is 800, so it's height 8. 0, 8, 0. So this is the trilinear coordinates from part 1, yeah?
Very fast coordinates.
Well, they're not exactly the same. Okay. And so, for example, this would be like, so if you split them up. Whoa, what the? Like that, yeah? Yeah. What the? No. Yeah? I'm kind of confusing myself. Yeah, when you make those lines not straight, these ones end up.
That one sleeping.
Yeah, so can you see the distance from A? That was X, right?
Mm-hmm.
So that's like, X equals 0, X equals 1, X equals 2, right?
Yeah.
That's like 2, and then they said it was 2, 60. Yeah. 260 because it's 6 units away from, where's Y? Which one is Y? It's B? It's B, right? C. So B is like 1, 2, 3, 4, 5, 6, yeah?
Yeah.
Okay, and it's no units away from the C base, yeah?
Yeah.
Okay. Okay, I don't want to label too many. If you get the point, that's fine, yeah? Okay, for instance, figure 4.6a and b illustrate problem 8763. So we have 8 pints altogether, and we want it to be 7, 6, 3. Okay, so that means we have to be inside a. So 7 means it could be up here, right?
Yeah.
That's 7. 6 is here, yeah?
Yes. Good.
It's the one we drew.
Mm-hmm.
And 3 is like 1, 2, 3, yeah? So this is the hexagon that we're talking about.
Mm.
Yeah, so we proved before that the height always adds up to x plus y plus z, yeah?
Mm-hmm.
So we know as long as we keep it in here, it's going to be fine, yeah?
Yeah. We can make any value in there. But we can't make anything.
Yeah. Okay, so what's the plan here? So distributed in this manner, and we wish to measure out 4 pints. Yeah?
Mm-hmm.
Oh, we want to measure out 4 pints. Oh, I see. So you have these capacities, yeah? And you want to get 4 pints.
Yeah.
So I guess you want to end up 4 pints. Well, it can't go inside B, right?
Mm-hmm.
So you want the 4 pints. Yeah, so the operation is pouring completely, making one full or one empty, right? And you want to get 4 pints, so 4 liters or whatever, 4 units of something. And in some sense, you don't have to be exact. You can just have a really small triangle.
Yeah.
But there's a thing called Sperner's lemma or something that's like got a pretty cool proof. Cake division and stuff. Yeah.
Yeah.
There's always an optimal sharing, no matter how people value the cakes. Yeah. And so, what are we doing again? 4. We're looking for 4, for example, yeah?
Mm-hmm.
So what does that mean? So it can't go inside the third jug, yeah?
Mm-hmm.
So we're looking for either A or thingy equals to 4, yeah?
Yeah.
So does it illustrate that? Okay, it doesn't, but we could obviously illustrate it here, yeah? So A equals 4 is 1, 2, 3, 4, yeah? So it's like, let me draw it in another color. Blue, yeah? Yeah? And B equals 4 is, oh, so this is some kind of like crazy moving thing. Okay, so B equals 4 is,
The one.
I mean, Y equals 4
Yeah. There is very specific.
is 1, 2, 3, 4, yeah?
Yes.
Yeah? That makes sense?
Mm-hmm.
So I understand this to mean that we have to end up on one of these blue circles.
Yeah.
Yeah?
And that one. The one on the bottom. Also. Yes.
Thank you, sir. Ah,
Mm.
so,
You can only move along the line and onto the boundary.
yeah, so there's no point crossing here, right? We can only go to vertices on the graph.
Yeah. You can only, and you have to keep going until you reach the end.
Yeah. I guess it depends where you start, okay? So,
Mm-hmm.
I mean, it feels different if you start in here and if you do as outside here, yeah? But actually, it means if you just try all the possible ways, you'll eventually get it or fail, right?
Mm-hmm.
So at least that's putting like the problem into sort of a very, what do you call it? Like it represents the problem very well. Yeah?
But doesn't that mean you have to end up with one of the 3 blue circles, but one of the 3 blue circles on the boundaries, and you can't do it? If you're pouring, right? Like,
Yeah.
it doesn't really count if you're pouring through 4, right? Like, so if you started at 2 and you poured to 6, right?
Yeah.
That wouldn't count as reaching 4 because you can't, like, you wouldn't know where to stop. So, like,
Yeah, like you can't like if you have like okay, let's have an example, yeah? I don't think so. Do you want to start here, for example, or something easy? 260, yeah? How about that? So 260 means there's 2, 6, and 0 lines, yeah? So that's the example you were thinking of.
yeah.
So we can't pour 2 into 6, yeah? It's full.
Mm-hmm. We can only go.
So where can we go? We can go 2 into 0, yeah?
Yeah.
6 into 0, or 6 into 2, yeah?
Yeah.
So we have the choices of ending up at
You can go up to the right or like down to the
yeah. You could do nothing.
Alright.
You could put 6 here, so you end up with 7 and 1, right?
Yeah, which is unfair.
Okay. So 7 and 1, yeah?
Mm-hmm.
Oh, that's what they mean by the diagram. Yeah, they drew it for us.
Oh,
Okay, you go 7 and 1. You could go 6 and 2, yeah?
yeah.
Oh, so that's what you mean by emptying, right? It's in the boundaries.
Yeah, you have to go until you reach the boundary.
Yeah. So if you're emptying, so something has to end up at 0, right?
Mm-hmm.
Or full is you end up at one of the red
Yeah.
lines, yeah?
Mm-hmm.
Oh.
Yeah, so like you just keep like bouncing around, like, or you gotta choose some directions, but like,
Yeah. So
yeah.
this is saying the problem is impossible to solve.
Yeah, well you can only end up at like the three.
The vertices.
Yeah.
The vertices of the hexagon.
Well, no, no, not really, right? Because if you go to the right,
Okay, let's see. Where do we go? So let's go make. Oh, maybe it doesn't empty completely, yeah? So
yeah,
what happens? It can get full or it can get empty.
so you like,
So 0, 6, 2, for example, yeah?
mm-hmm.
So that's here.
Yeah,
And then you can go to here, which is, what's that? You can put 6 into 2, right?
yeah, 0, 5, 2.
So,
Yeah, but those aren't the only possibilities. You can pour the 6 into the 3, right? And that'll make 2, 3, 3.
hold on, 6 into the 3.
Yeah, from 2, 6, yeah. You can pour like 3.
I can go here, you know,
Yeah, yeah. So like you can travel along any line.
But you have to go all the way.
Yeah,
Oh, okay. So you can end up
through that. Yeah.
here.
Mm-hmm.
Yeah. Oh, and then you can end up like here, for example.
Yeah, so you just keep traveling this line. So, yeah.
So you can solve the problem then.
But there are a few apparently that
So you can have a better chance at least. Okay, so let's see. You can go there, for example. Go here. Go here. Oh, how come there's a red line here I didn't draw, is that right? Yeah, then you go here, then you down here, and then you get to here, right?
Oh, yeah. So that one. But it says, it tells you that the points 0, 5, 5, 5, 0, 5, and 5, 5, 0
are not reachable. Oh, that is so cool.
How is this related to this topic of geometry?
Geometry?
Like this book.
This book. How is geometry related to geometry?
No, like how is this formula related to geometry?
Or the height of the triangle. This is a topic in chapter 1. Was like pedal triangles. We didn't really cover it that much though. Okay, let's see what the book says. So, so figure 4.68 draws attention to the point 332, which represents typical state. 3 in the first, in the second, and 2 in the third. The broken lines, blah, possible operations, blah, blah, blah. Yeah, it's explaining all the stuff we just did, yeah?
Yeah.
The hatched lines in figure 4.6b show one of the various ways of passing from 332 to 440. Okay. Thus, dividing the 8 points into 2 equal portions, the whole path is a broken line, which proceeds always along direction parallel to one side of the triangle of reference and bends only when it reaches the side of vertex of the hexagon. Yeah. Oh, so it's like a billiard, some kind of weird billiard ball thing with choices.
A human billiard ball.
Oh, okay. So the middle ones are impossible, yeah? It has to be these three.
But you can start there.
Oh, yeah.
If you want to.
It's like so, like, what's the opposite of cheating or pointlessness?
Or like,
It's like, start at a super solution,
right.
approach a
You
weak
have reached
solution.
your solution.
You have reached an inferior solution.
Whoa.
Okay, so it follows that for 8763 problem, any whole number of pints less than 8 can be measured out. Whoa. Whoa. Is that true?
Probably requires extra testing.
What's the condition on the starting?
Could be anywhere inside.
Be anywhere inside the thing?
Yeah.
Oh.
Anywhere on or inside.
I guess starting anywhere inside is kind of equivalent, unless you're already finished, it's equivalent to starting on the outside.
Yeah.
Because after one step, you'll be on the outside.
Yeah.
Like, you don't get it. Oh.
Well, you have like 6 ways to go. So, like, you can.
Yeah.
Like, it's basically the same.
Yeah, like without lots of generality, you can start on the red line, yeah?
Yeah, unless your first step is the solution.
Yeah, so that's nice, because it kind of solves the whole family of solutions, right? Of problems. Did we verify that any size can be measured out? Okay, so anything in the perimeters can be measured out, right? What's the perimeter? That's obvious. You can always just cycle around, yeah?
Yeah. Oh, yeah.
So what's that? That's 7. What's that? 7, what's this? 0?
0, yeah.
0, 1, yeah? And what's this?
It's 5
Are you just reading?
Yeah, I mean,
503.
Yeah, that's all 6. So we know we can make 1, 2, 3, 5, 6, 7.
So you can make 1, 2, 3,
5, 6, 7. Just, yeah, 5. So it can be in any.
Oh, okay. So 4 is the only one that's tricky, isn't it?
Yeah.
So we got 1, 2, 3, 5, 6, 7, and 4. That's why we did the example 4, because that was not there, yeah?
Yeah. And you can't make 8.
So they said 4 say. It was actually more than just a random 4. It was like the only one that wasn't obviously possible, yeah? Actually, I remember, so now speaking of Barry back, okay, I have this one memory of this event, okay? Like at Sydney Uni, they made you join some golden tea society. There's the biggest BS society, whatever, right? And like there was one event that I decided to go to, and it was like Bob Carr was there. Have you heard of that guy? Okay, when I was young, he was the Premier of New South Wales. Okay, so he was there, and this guy was called. He gave me this idea. He was pretty strong, you know. He had a strong speech about him, yeah. And this other guy, he was like a science guy. His name was like Barry, actually. Okay. And then like, so we're all listening to Barry talk, okay. And Barry was like, so it made me think, because I don't know if my microphone's actually catching the stuff I'm saying, right? But he's just saying some stuff, and then we don't really know what he's saying. And then Bob Carr's just like, speak into the microphone, please, Barry. It was like somewhere in the middle, as if it was like only we missed all of it anyway. So it was just like it was really funny. Okay, it would be funny if you knew who Bob Carr was, but speak into the microphone, please, Barry. Barry. So that's my example of a Barry back, I guess. Alright, so now we can easily measure out 1 pint, 2, 3, but never achieve 5. Oh, this is 4.6C.
Yeah, with 10, 8, 7, 6.
Oh man, I have to draw another one. How much value do I get out of this diagram?
Yeah, you
10 is good, yeah?
Yeah, you make it bigger.
D is used again. So
You can rub out some. Oh, you don't need to rub out
yeah, let's just see what happens. So that's 8 so far, right? I need 10.
that. 9, 9. Not
2, yeah?
Yeah.
That should be enough, yeah?
Yeah.
So this is now, the coordinates are now awkward, right? Because 10 is 2-digit number.
Yeah.
So let's just not write those. Oh, then we can't, these coordinates are all different now, right? At least the 0 ones. Well, should I have added it in another direction? No, it doesn't make a difference, right? Okay, that's still 7, yeah?
Yeah, those ones are definitely wrong.
The 0 is not right, yeah?
Yeah, that's 3.
The 1 is not right. The 7 is still right, yeah?
Yeah.
So the ones that we're counting from that way are still okay. Alright, let's not be lazy here and just... Okay, I don't know why I said let's not be lazy here and,
I'd be lazy.
and became lazy. Okay. 10, 8, 7, 6. 10, 8, 7, 6. Okay, so 10 pints, 8, 7, 6. Okay, so what would the red be now? It's 8 now, right? Like that, yeah? 7 from B would be bottom left. B is
Yeah, so it's
Oh.
3.
Okay. So here, right? 7. And then what was it? 6. Is this already 6? Huh?
Yeah, 4 from
2, 3, 4, 5, 6. Yeah? Yeah. Yeah. Okay, now we can easily measure out 1. 1. Wait, what are these coordinates? Easily measure out 1. 820, yeah? 802. 70.
703.
But it's not 7. It's 0 something.
Oh, yeah, 0, 0, 7, 3.
Right, this is 0. Mm-hmm.
Yes.
There's a 0 in the middle somewhere. So this is 0 at the start, this is 0 in the middle.
4, 6. Yeah. Oh. One of these 4 and one of these 6.
Why does it say we can easily get 1? Oh, you pour the 7, 8 into the 7.
Yeah, you just like, you start with like 2 8s there.
Yeah, you fill up the 8, right?
Yeah, and then
you fill up the 8. You pour out. Can you empty the 7? Wait, you don't have 8. Oh, you have 8. Yeah, you fill up the 7.
Yeah, you just
and empty out the 6, right? You fill out the 7, empty out the 6, and then you pour it all into the 6, and there'll be 1 left over, yeah? Okay, so you can easily get 2 or 3 or 4, but you can never achieve 5. Oh, we can try to figure this out ourselves. So wait, we can get 2. How do we get 2? Yeah, it's on the outside. Yeah, 3 is there.
And 4 is there.
There's 4 there as well.
The missing.
Missing. Which one's that?
It's just 6.
This one?
Oh, actually, it says it's 46.
4, 6. Yeah.
Yeah. Now it's 4, 4, 6.
Yeah. So this is 1, 2, 3, 4. Yeah. And then 6. 4, 0, 6. Okay, so that means we can get 1, 2, 3, and 4, 6, and 8, yeah?
Yeah.
So the only thing is missing is 5, yeah? And it's impossible. Impossible. You just get a triangle in the hexagon with vertices entirely on the side, so nowhere to bounce into. All solutions are enclosed by the triangle. Yeah, cool. The chat is with us.
Yeah.
I guess people aren't chatting because, well, I'd like to think it's because they're thinking, but in reality, maybe they're AFK. Okay, so trying to get 5, yeah? So where is 5? 5 is 1, 2, 3, 4, 5. It's here, right?
Yeah.
Oh, 1, 2, 3, 4, 5. It's here, yeah? Yeah? Wait, that's 4. I just circled a 4. That's a 5, yeah? Wait, it's the same one. Yeah, okay. And then another direction. 1. 1, 2, 3, 4, 5. Oh, so it's a triangle, yeah?
Yeah,
it's an equilateral triangle. Oh, it's a closed orbit, isn't it? Yeah. Oh, is this what Sean was saying?
Yeah, that's
it. Just bounces around here, isn't it?
Yeah, so there's no chicken. According to the book, which runs round and round like a vicious circle.
A vicious circle, why?
I don't know, that's what they call it. It runs round and round like a vicious circle.
Yeah, so I guess another way to express it is each move is also reversible, right?
Oh, apart from the first one.
Yeah. So the only way to get to one of these is from here, 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 and here, right? Like the only way to get to this one.
Isn't it only... No, you can't get there from A to 0.
Oh, sorry, I was reversing it.
Oh, yeah.
But
yeah, unless... Yeah.
Oh, so the only way to get into this spot is from here and here, right?
Mhm.
But the only way to get into these spots is from here and here as well.
Yes.
So that proves it, yeah?
Yeah.
The only way to get into that is to start in there.
Mm-hmm. Vicious circle.
Vicious. Some kind of, what do you call it?
It's gonna attack you.
It's not vicious, it's like, maybe, what do you call it? Wow, what's that word?
It's like a
Yep.
dog with chasing.
It's like they only let family members in.
Oh,
What's that called? It happens in Australia a lot.
it does.
Nepotence? No. Oh. This kind of phenomenon arises in any problem where 2D is greater than everything, but D is less than everything. Well, that's a claim.
Yeah, because there'll be a point between, like, as long as it's like an equilateral triangle that looks like that, that
Yeah.
will happen. So, like, if none of the points are larger than 2D and none of them are smaller than 2D, they'll have to be triangles. Things like that. Like, one of the. Yeah.
Oh yeah, so you understand that?
Yeah.
So will you explain a little bit more? So
Like, if all of them are between D and 2D.
yeah. And D is the amount you want, right?
Yeah.
That means D will fit nicely inside.
Yeah, like, because it's larger than D, like, all of them will, like, enclose D, and since they're all smaller than 2D, like,
I guess yeah, so if a D is small enough it'll be a triangle, right? If it's too big it'll turn into a hexagon.
yeah.
But what's with the 2D business? Oh, that's maybe, so D is too big. D is too big. That's like outside, right?
Yeah, yeah, no,
I don't know if that requires justification. If a ball was to bounce, so this is what Sean says, if a ball was to bounce into it, it would stay in there forever. So there's no way it could go on. 2D equals minus A, D equals C. It can't be done by the difference. D is less than C. D is the amount. So A is that height, yeah? So for D to be, was it bigger than A, was it? 2D is bigger than A. That confuses me. But D is smaller than C, I can understand that, I think. D is smaller than C means it fits entirely inside the hexagon, right?
Mm-hmm.
2D. What's 2D got to do with it? Two D equals minus x greater than or equal to minus equals greater than or equal to A. Maybe we can do an example, yeah? So something where 2D is greater than or equal to A. So okay, let's check it's true for this example, yeah? So D was 5, right?
Mm-hmm.
So 2D is greater than, what's A? 7, right?
Yeah. 6, 7.
And then,
Yeah, they're always between 5 and 10.
hold on, but A is not less than 3. Let me erase that one. So 5 is less than everything, and 2 times 5 is 10, right? It's bigger than everything.
Mm-hmm.
Yeah, I don't understand the 2 times business.
Mm.
Why is it 2 times? So the D less than everything, I guess, is under these lines, yeah?
Maybe try an example, like D equals 3.
Okay, so D equals 3, it doesn't meant to not work, right?
Mm-hmm.
So D equals 3, well, not like this anyway.
Yeah.
So D is smaller than all of them.
Oh, it's because like it
Where's
would be
3?
outside.
Oh, it's still outside, is it? So 3 is here, right?
Mm-hmm.
Yeah.
Yeah.
Wait, is it? Wait,
Yeah, that's 17.
it's 3 from somewhere. 1, 2. Oh wow, that scale is bad. Okay.
Mm.
3, 3.
Wait, now is it 6? No? Wait, what? Are there not 6 points?
Oh.
Wait, what? Wouldn't that be true? Like, even if you had D equals to 3, and you had like A, B, C be like 4, 5, 6,
Yeah.
would that still.
You need them to repeat, I guess, to coincide, huh? Something about Sean said something about the difference. D minus, like D is less than. No, it can't be done by the difference. Wait, where else is 3? 3 is here, right? Right, so if 2D is bigger. Oh, wait a minute. Uh, Oh, I think I understand why the 2D thing now. It's because I think it relies, so it's not so that you get the solution, right? Like once you get the solution, yeah, you have a D, yeah,
Mm-hmm.
right? I feel like, oh, it makes me feel like if you have a D and you want to pour another D, right, it won't get into another valid place. Like,
Mm.
what are these coordinates here? What are these coordinates? 5. What are these coordinates?
5, 5, 0.
5.
5, 0, 5.
Yeah?
5, 0.
So there's 2 Ds, yeah?
Yeah.
So you can't pour one of them into the other one.
Yeah.
Because that's twice D and that's bigger than A, right? So you can't pour this into that one and get another solution. So they have to keep staying inside.
Yeah, so if it was smaller than that, then like if you had like 3, 3, like 3, 3, 4, for example.
Yeah.
Then you could like pour the 3 into the 6 and then
It comes out, right?
yeah. I mean, it seems like
Yeah, so the 2 Ds interacting is what leaves the solutions, right?
mm-hmm.
So if they can't interact, then they keep cycling, because
Yeah.
that'll have to pour to the 0,
Yeah.
and you get 0, 5, 5, right?
Mm-hmm.
So if you're allowed to pour into each other, then you lose the 5 and you lose the 5, yeah?
Yeah.
But if it's bigger than the size of the jug, you can't pour it, right?
Yeah.
Actually, what happens if you pour 550 to
Oh, you still can pour it, but like there's no way to get back. Which is kind of the point. Like if you pour like a 5 ton.
Oh, then you're just doing boundary, yeah? Then you're just back at the boundary.
Yeah, you can't get back to it.
What does it mean? If you could pour 5 into another 5, yeah? Then yeah, so D being smaller than the last one means you can always pour to the third thing, yeah? So you can always keep pouring around. If it's too big, you can't pour them together, yeah? So if you try pouring them together, you always get a starting vertex, yeah?
Yeah.
And we basically already discounted those. I think that's pretty good as far as using all the information to explain it. Okay, we're almost done. Ooh. A slightly different kind of anomaly occurs in the problem 10864. What happens at 10864? In which the paths that visit 550 form a pattern of small equilateral triangles and regular hexagons. Ooh. This illustrates the obvious fact that an odd number of pints can never be measured with vessels whose capacities are all even. It's obvious. Because every time you pour, it's an even change.
Oh yeah.
It's invariant. Such troubles can be expected for any problem where they have a common divisor, yeah? I guess it's just another way of explaining it. The most famous problems are those in which A equals 2D and B plus C also equals. So the most famous ones. Let's get straight to the most famous ones. See, actually, if you didn't take the time to understand the previous stuff, it does slow you down a lot, I'm pretty sure. So it's H equals A. Wow. What? H equals A. What does that mean? Oh, okay. A has the capacity. It's not like it all goes into A, yeah? A has capacity H, and B plus C have the same capacity as A. So that the domain of operation is bounded by the parallelogram whose vertices are. Oh, it's kind of getting a bit more general. So so A can be the whole thing, right? So it can go all the way up to the top, yeah?
Mm-hmm.
And then B plus C has to add up to A. So that means B plus C is constant, which means they lie on a line, yeah? Depending on what A is, yeah? So if A is that, no, it doesn't make sense. What am I saying? So For example, if A was 10, B and C have to be 5, don't they? No, they don't. Like one of them has to be like, oh, it doesn't actually say what the capacities are. Oh, okay. Hmm. Parallelogram A00. So that's that one, right? A00. CB0. Mm-hmm. Oh, okay, yeah. So at least when B is 0, when Y is 0. I'm getting a bit lost. Just wait. So it's saying A00, CB0. So 0 is this, it's on this line here, CB0. Do I just write that anywhere? CB0. 0 BC and B0C. 0 is here, BC, and then B0C. Yeah? That's a parallelogram. (4.6) and F now show the 8-step solutions of the problem 8853. 8853. Okay. Which can be expressed as follows. 2 men have a vessel filled with 8 pints of liquid and 2 empty vessels with capacities of 5 and 3. They wish to divide 8 pints of liquid equally. What was D? Oh yeah, D is half of A, right? Yeah. So they have 8 and they have 5 and 3 and they want to share the 8 equally.
Mm-hmm.
Yeah. But what if only one of them comes up with the idea? The other one will have to owe him or her. Okay. Oh, so there was an exercise I had in my AIMO thing where it's kind of like this. So this kind of problem, without knowing all this, is an example of is essentially a chase, right? You have two things you can do at any given time, so you just try them all out, right?
Yeah.
That'll work. It's kind of like a case bash / chase. 853. The first move must be to fill either the 8-pint vessel, the 5-pint, or the 3-pint vessel. Yeah. So maybe we can draw that here then. That's 8. Let me draw it. That's 8, 0, 0. Oh, this diagram is inappropriate for 8, 0, 0. It's more like here. We regard that line as a mirror. In other words, we follow the path of a billiard ball which is struck so as to start out along one edge of a table having its somewhat unusual shape. The rule of successive reflections is justified by the fact that each piece of the broken line being parallel to a side represents the act of pouring. Oh. So if it's parallel, it goes here. Oh, so it basically keeps reflecting. So it's meant to reflect off the edges until it, or slide along the outside, yeah?
Yeah.
Okay, that's what happens with a parallelogram. Okay. Well, the third remains. We thus obtain the 7-step solution. And the 8-step solution. Clearly, such a problem can be solved whenever the integers b and c are co-prime. That is, they have no common divisor greater than 1. Yeah, so I guess they're co-prime. The reflection is meant to hit everything, yeah? Yeah, you can model out like the sum of these ones plus the sum of these ones. You can solve that equation basically. Oh, okay, AX, BY equals what? Or maybe it's B and C. C. That's kind of cool. So the example you can pretty much just follow on your own. You want to have a look at the book. It looks like that. Yeah, so is it obvious if it's co-prime at work? B and C are co-prime. Yeah. Yeah, I guess it kind of, it doesn't lead me to want to investigate it for some reason. But I think, yeah, like it's kind of eased us into finishing because, yeah, like the way of presenting problems in this way and then solving them in this way is pretty cool. Yeah. I guess it kind of allows you to solve more than one problem at a time. You can solve a whole family of problems.
Yeah.
Okay, let's leave it there. Maybe as an exercise, someone can explain to me why them being co-prime will always lead you to a solution. I guess the premise is when that's like that, yeah? Okay. So B, C co-prime gets or D, yeah? It's kind of, so yeah, the D is already specified, so it just means it's solved, yeah? So it's B, C co-prime works, is what the claim is, yeah? Okay. Yeah, if you wrote it up, I would read it and mark it.